Classical Physics Tutoring, Chapter 6, Section 1, Correcting Classical Physics. Okay, so we cover basically everything in the classical physics so far. It's starting with Newton's law, and we expand it into fluid dynamic, and we use Euler's method to describe the motion of the fluid, not the Newton's original motion of the mass. The motion of the mass, you have a motion. Fluid dynamics, we use field theory. And we added thermodynamics, law. This is about energy and define the temperature. And we also added Maxwell's equation. So this is the range of classical physics, and everything works so far, although we can't explain why the vacuum space has a field like gravity field. We talk about field theory. The fluid dynamics field theory is very direct. It's a movement of mass. The original Newton's idea, the mass. It's just continuous mass moving. But the gravity field and the electric field, magnetic field, the field contains energy, and how the vacuum space can have energy. It's kind of, outside of classical physics. This, even the modern physics, we can't really tell what they are, but it works very well so far. Okay, and now there's a nagging questions. Maxwell's equation derived at the light speed. Well, this microwave and anything else is the same thing, right? Well, gamma ray, X-ray, it's all EM wave. And this light speed seems to be independent. Say you have A moving at the V speed and emit the lights, and this light speed, you have an observer B, look at the light, it's supposed to be plus C, right? But it's not, it's only C. So there's such a problem existing. So another problem is the energy of the wave. Instead of regular wave that propagate on the medium, the EM wave has energy, just like a quantum. So it's opening up the new physics, okay? And it's beyond the classical physics. However, it used to be beyond the classical physics. However, this light speed, this issue, it's investigated by Einstein, and Einstein proposed the special theory of relativity, and that used to be outside. Now it's included in the classical physics because it's well established theory. So we are adding Newton's thermodynamics, Maxwell's equation, and special theory of relativity in the classical physics. And this is the way currently most of the colleges organize a physics course. So you have to cover this, and this actually cover only half of the story. There is another one called General Theory of Relativity, but that requires additional math tool, which is not in the undergraduate. The math tool also, that kind of math tool used only for physicists. So we will include only the result of the theory only in this classical physics general. And general theory of relativity is we don't get into the fundamental equations and derives other stuff kind of things, because it's basically the math required. Okay, so we will include this into the classical physics. That's what you're going to learn. And this chapter is about this last special theory of relativity. And what's happened is speed of light. There was a proposal. Maybe light is the wave in the medium, but vacuum, what kind of medium? And they call that ether. Ether filled everywhere, including vacuum. So that's why light can propagate as a wave. And this has a few problems. Like, you check the Doppler effect. The light Doppler effect is different from other wave medium base. Okay, so it's not exactly the medium wave. Also, there are a lot of quantum behavior. Which cannot be explained by assumption that the light is wave. And the scientists struggle with this duality of characteristic. The light is sometimes wave, sometimes quantum. Quantum means the particle behave like a particle, sometimes behave like a wave. And this has been the problem. So we needed to go back to the basic of Newton's law. Maybe as far as we stick to Newton's law, we can never solve this problem. And coming to that idea, we examined what's wrong with Newton's law. Well, Newton's law has an unwritten assumption. It's called absolute space and absolute time. And what it is called Galileo's rule. Means if A is moving at the speed v, and emit the B at the speed w, then B's speed is v plus w. And for example, say a boy tossed the ball in the train, and the man standing on the platform, and the boy see the ball just go up and down. The man see the ball move like that together with train, right? So for this man, the ball is moving at the v plus w. This train is moving at the v, and the boy toss the speed, horizontal speed is w, right? And if boy toss it just upward, then w is 0. So he still see v portion of the ball, but the boy doesn't see the w is 0. Boy just see a ball goes up and come down. It goes up and comes down. That's only motion the boy see. So observer see different things. Now observer see different things is okay with the science, because science say, hey, this is a rule, so we translate the speed, then it's not a violation of physics law. We can use exactly the same physics for boy and the man. Same physics law applied. Although they see two different things, same physics law applies. Okay? So we are translating what man see into what boy see, and when we translate, we are using this assumption. There is absolute space. Absolute space means somewhere in the space has a reference point, and if A is moving at the B and B is not moving, you can tell, yeah, A is moving, not B. But B see A is coming close, say B is here, right? So B said A is moving, but A sees a B and see B is moving. The who judge who is right? This guy, absolute space, reference point, can tell the guy moving is A, not B, right? So we can do correct translation, and by translating, the same physics law apply to A and B. Okay? Now we have a problem with the time too. A has a clock and B has a clock, and how do you know they are completely synchronized? We can't tell if A and B are separated, because when you look at A's clock and B's clock, who is correct? There's no such a thing like absolute time, right? There's somewhere in the universe has a clock and tell you, hey, this clock is fast. No, this clock is slow. There's no such things. Only things we can tell is, okay, time interval AC and time interval BC, are they same? But that is even harder, because as soon as you try to compare, the time passed already because of the distance. They are in a different place. So time too, we will include the time also in this issue. The space, who is moving, if you know who is moving, we can translate the equation, right? The equation of motion. Then the same physics law apply to A and B, and Newton's law apply for both. They see two different things, right? A is moving, but A thinks B is moving. But you can easily translate into A is moving if we know what is not moving here. Reference point. You get that? Okay. So there is an assumption that Newton's law can translate every observer using absolute space and absolute time. There is somewhere we can tell which clock is moving faster. So we make a correction. Which clock is moving slower? We make a correction. And who is moving? From this reference point, this is absolute space is not moving, no matter what. Okay, so every motion is measured at this reference. Okay, so we need these kind of things in the Newton's law to translate between observer, because each observer see different things, and in order to apply Newton's law and they are consistent, the physics law has to be working for boys and men both. The speed, coordinate, everything has to be translated using this absolute space, absolute time. This is the basic premise of the Newton's law. Okay, now here's the idea that most of many people are having a problem is, okay, absolute time, absolute space, we get rid of it, and can we still make the physics law working for boy and man? Okay, we don't need to translate what they see. They see two different things using absolute time and space. We don't need this. Instead, we make it very even. They are just relative, and no jury or judge to decide who is right. We don't have to decide. We just say boy see this way and the man see this way, and we can still translate. So it's become relative, not absolute. Okay, the name relativity theory come from here. We get rid of absolute space and time that is needed for Newton's law. Galileo's rule used that to translate the observers. So every observer see different things, but if you translate it, then they are same physics law. Okay, now we change a little bit here. We don't use this absolute. There's no absolute reference point in the space. Where? Around the sun or maybe Earth. We don't have that kind of things. Absolute time, there's no absolute time. There's no clock, universally correct clock. So we get rid of those. We do somehow cleverly translate what boys see into what man see, and examine the physics law. If physics laws works, then that's okay for physics law. The physics law, most important thing is it's consistent to every observer. Okay, consistent to every observer. It's getting a little bit philosophical, but that's what we try to attempt. So we go back to Newton and flip the basic assumption of absolute, which is used for translation of observer. What the observer see, what the one man standing on the platform, we translate into the boy. Then you understand using physics. Or vice versa, we translate boys. Using absolute space and time, we can do this. We get rid of this. We try to do translation without absolute. So we use relative translation method. And I don't know why they don't write this way. It's much easier to understand the relativity theory by approaching this way. This basically, observers see different things. To examine the physics law is consistent on both observer, we translate their coordinate and time using relative translation. So nobody help you like, okay, here, this is not moving reference point, use this one. No. Here, this is a clock, correct. Use this clock. No. We don't need this help. We just translate it. And basic translation using relative relationship. That's the special theory of relativity. And why is special? It's covered only for inertia speed, means A and B, the B is moving at a constant speed against A. This case, okay? Now, if B is moving against A with acceleration, then it's not special theory now. It's going to be general theory of relativity. Okay, so from next video we talk about this, and as a result the stuff you know very well, like E equals mc square and many other things you've heard about, it's all come out from here. Okay, so I hope you like this video and continue to watch next video. Please subscribe.